Hello and welcome to Bedroom Physics. Today I'm going to be talking about fluids, and there's a couple of things we need to know before we start. Number one is that a fluid is described as either a liquid or a gas. Number two, density is mass over volume. Okay, now that we know these two things, we can jump right in. When a body immerses itself inside of a fluid, the fluid has a perpendicular force that acts on all parts or all points of that object or body. Take, for example, a surface like this. If the surface is to remain at rest along with the fluid, then the forces that are acting on one side of the body has to equal the forces on the other side of the body. Of course, this surface has an area, so the forces on the entire area have to equal the forces on the other side of the entire area. This force over an area is known as pressure, or the change in the perpendicular force from the fluid over the change in area. The unit for pressure is the Pascal. Now, pressure changes as you go deeper in the fluid because we have to consider the weight of the fluid. As we go deeper in the fluid, the volume above us gets larger, and since density is mass over volume, it would mean the mass would be increasing, and so therefore the weight would be increasing. Let's examine a small patch of fluid within the fluid. If we have a rectangular part of a fluid with some volume of a fluid, on the bottom of it, there would be a force being exerted on the bottom area, there would be a force being exerted on the top area, and forces all around it which cancel out, and of course the weight of the fluid itself. Now, the bottom force is going to be represented by pressure times the area. Now, this pressure is at this specific depth. Remember, the weight changes as we go deeper. But then the force up here is represented by pressure plus the change in pressure times the area. Of course, if the fluid is to remain at rest, then the sum of all the vertical forces will equal 0. Before we do this sum, let's remember a few things. Number one, dV is equal to a change in y. As you can see, the area is not changing, but rather what's changing is our altitude or depth. Change in mass is going to be equal to the density times the volume. And we know that change in volume is equal to A dy, so dm is equal to rho A dy. And change in weight is going to be equal to change in mass times gravity, and we know that change in mass is equal to rho A dy, and so change in weight is going to be equal to rho A dyg. Now we can finally add these all up, and we'll have the sum of the forces in the y direction is equal to 0, which is going to be equal to the pressure times the area at the bottom, minus the pressure plus change in pressure times A from the top, minus the weight, which is going to be rho Ga dy. And if we solve for change in pressure, we'll see that it's going to be equal to rho A dy. Take note that the change in pressure is not dependent on anything else except the change in y. And from this we can conclude that the pressure at any 2 points, or in fact any point on the same level, are going to be equal. This also leads us to the conclusion that the pressure at a point in a fluid is equal to the pressure at the surface of the fluid plus the pressure as a result of a change in height. And this leads me to Pascal's law, which states a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. The best way to exemplify this is using hydraulics. Take, for example, body of fluid inside some sort of container. On one end, we have an area which there's a force being applied to, and of course the fluid is also applying force back. And on the other end, we have a larger area with a force being applied to it and also a force being applied to it back. Since the pressure is transmitted undiminished, if we push down here, the pressure that we cause will be exerted here equally and to all points of the fluid. This will give us the equality that pressure is equal to F1 over A1, and it's going to be equal to F2 over A2, meaning that we can essentially amplify the amount of force that we put in the initial force, and so long as we are pushing on something with a greater area, then we can cause a much greater force on the other end. Moving right along to buoyancy, we have Archimedes' principle, and it states, any object totally or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. For example, if we have an object within a fluid, the buoyancy force is going to be equal to the volume that the object displaces times the density of the fluid times gravity, and is going to be opposite to the weight vector of the object itself. What can we infer from this? Well, if the object is in equilibrium in the fluid mass displaced will equal the mass of the object. After all, if it's in equilibrium, the weight and buoyancy will be equal to each other, g will cancel out, and all we're left with is the mass. However, if it is not in equilibrium and the object is fully immersed, the fluid volume that's displaced will be equal to the volume of the object. Now, I've been talking about fluids at rest. Let's talk now about flowing fluids. When a fluid moves, the one thing that doesn't change is its mass. At point 1, the mass will equal m1, and at point 2, the mass will equal m2. Now consider fluid flowing in this pipe. First of all, at one end, we have area 1, and the fluid at this point is moving at velocity 1. And the fluid is also taking up volume 1, and the distance that it's traveling is going to be equal to the velocity times the change in time. On the other end, the fluid is moving at velocity 2. The cross-sectional area of the tube is going to be equal to A2. The change in volume is going to be change in volume 2. And the distance that it's traveling will be equal to velocity 2 times change in time. But we know that the mass at point 1 and point 2 will be equal. So there is an equality here. Well, volume is meters cubed. And we have an area, we have a velocity, and we have a change in time. If we multiply the velocity times the change in time, we get back a meter, and area is meters squared. So we can get the volume from AV dt. And remember that density is equal to the mass over volume. So if we multiply the density times the volume at point 1 and point 2, they should be equal to each other. Now, of course, if the fluid is not compressible or incompressible, then these densities will be the same, and they will just cancel out, leaving A1 times velocity 1 is equal to A2 times velocity 2. Of course, if the fluid is compressible and the densities perhaps change from point 1 to point 2, then we have to keep up the densities, and the equality will be density 1 times area 1 times velocity 1 is equal to area 2 times velocity 2 times density 2. The last thing that I want to talk about is Bernoulli's equation. Now, say we want to solve for a flowing fluid where the area is always changing, the velocities are changing, and a bunch of different things are changing. Well, we can describe this flowing fluid using work. Now, remember that work is force times a change in distance. Well, we have pressure and we have area, which gives us a force, and we also have change in distance. So we can calculate work using this information. So we have pressure 1 from the first end. Of course, there has to be a force pushing the fluid through, and on the other end, there is a force opposing the movement of that fluid as well. So we'll have the change in work is equal to the pressure at point 1 times the area at point 1 times the change in distance at point 1 minus, since they're opposing each other, the pressure at point 2 times the area at point 2 times the change in distance at point 2. Of course, area times change in distance is change in volume, so we can simplify this to P1 minus P2 times dV. But there are other forms of work as well, like mechanical and gravitational energy. And so we can set P1 minus P2 times dV equal to 1/2 mass times change in velocity squared. Of course, mass in this case is going to be the density times the volume. So it'll be half rho dV times change in velocity squared plus rho dV, which is the mass, times gravity times change in vertical distance. And of course, since every term has dV, they will cancel out, and what we're left with is P1 minus P2 is equal to 1/2 rho times change in velocity squared plus rho g change in y. And that's Bernoulli's equation. Well, kind of. This is like the preliminary equation, but in my opinion, it's the most useful one. In any case, this has been Bedroom Physics. I hope to see you in the example video.